In the next 4 or 5 lectures, we are going to talk about a new topic called decomposition algorithm. So the idea of decomposition algorithm is to say that if you have a very large optimization problem, then you can decompose a large optimization problem into easily solvable, smaller optimization problem. And then you can solve those smaller optimization problems in parallel if you have a multi-thread computer. Right? And the advantage of that is to leverage things like parallel computing. Nowadays, even if you are looking at your laptop, you have multiple cores on your laptop, right? And now, we have things like cloud computing where you can have even, thousands of threads to solve those problems. So that's why today decomposition algorithm would be more relevant with the development in parallel computing. So in this lecture, we are going to talk about specifically decomposition algorithm for mixed integer nonlinear programming problem. Okay, so here, just to refresh your memory, this is a mixed integer nonlinear programming problem. You have nonlinear function, nonlinear constraints, and then we have mixed integer variables, right? So here we use x to represent the continuous variables, y represent the binary variables. Okay, so in most part of this lecture, we assume f and g are convex functions. Okay, so in other words, we are not talking about global optimization here, right? We assume all the nonlinear functions are convex. In the literature, usually people call this convex MINLP. And the algorithm to solve convex MINLP are older than the algorithm to solve global optimization algorithm. Right? So we will review a little bit about the history of convex MINLP. But in comparison, you may remember that when we talk about the global optimization algorithm like branch and reduce, right? The first branch and reduce solver was in the 90s, right? And so here we will talk about some papers from the 70s and the 80s to solve convex MINLP problem. So the history of this lecture is a little bit older than global optimization algorithms. And so we will mainly talk about 3 different types of methods: outer approximation, generalized Bender's decomposition, and extended cutting plane. Okay, so let's first talk about outer approximation, right? Just a little bit history. This was developed by Duran and Grossman in 1986. So Grossman was my PhD advisor. That's I would say that's his most significant paper in his whole career. It has around 2,000 citations, and it is one of the most highly cited papers in math programming. Yeah, so just to talk about the intuition of outer approximation before we go to the math. Here, if you look at a convex MINLP problem, as we said, the objective function is, let's assume it's a continuous function for now, right? It is a convex function. And then the feasible region is also, the relaxation of the feasible region is also convex, right? So you can think about this convex continuous region as some continuous convex functions, right? And then you have some variables that need to satisfy the integrality constraints. So you can think about in this convex region, there are a couple of integer points within this region, right? So you have basically if you relax the integer constraints, then the problem is a convex nonlinear programming problem, right? That's essentially what we are talking about. And the idea of outer approximation is saying that since you have convex relaxations, right? You don't really need to come up with convex relaxation anymore. The convex nonlinear relaxation itself is convex, right? And then due to the first order condition of convex function, we know that if you do the first order Taylor series expansion, those cutting planes always under approximate the objective function, right? So this is a property of convex function. If you do a first order linearization, it always under approximate the objective function. And similarly for the feasible region, right? If you do an outer approximation of the constraints, it always outer approximate. Yeah. So basically you can come up with a linearization of the constraints, and then you do not cut off any feasible points with an outer approximation. And that's just a property of the convex function. Okay. So as you can imagine, if you add, let's say for the sake of the argument, if you add an infinite number of outer approximation cuts, right? Let's assume for this convex region, at each of the boundary of this convex region, you add an outer approximation cuts, right? Then you are solving the original problem, right? It's exactly identical to the original problem, but of course you are not going to add infinite number of outer approximation cuts, right? So the question here becomes where to outer approximate, right? So can we just do a finite number of outer approximation cuts such that we converge to the global optimum of this convex MINLP problem? Okay. And of course, if you do the outer approximation, then you will end up solving a mixed integer linear programming problem, right? So then you can decompose a mixed integer nonlinear programming problem by a mixed integer linear programming problem. And also, you will see that in the next slide, we are actually decomposing an MINLP problem into two subproblems. One is a mixed integer linear programming problem. The other is a convex nonlinear programming problem. And for both of MILP and convex NLP, we do know how to solve them, right? Any questions regarding the intuition before we go to the math? Okay. And this algorithm is actually regarded as the birth of MINLP, actually. Before this algorithm was developed, people just treated MINLP as intractable problem. No one really started looking at those problems, right? So this algorithm gives you gives you an algorithm to solve convex MILP problem using the methods we already have, right? We already have an MILP solver, we already have an NLP solver, right? You can think about, you solve the MILP by a branch and cut solver, and you solve the NLP by some integral point solver, right? Okay. So let's talk about the so-called MILP master problem. This is so-called like a relaxation of the original problem, right? So you just assume we find a finite number of points, xk and yk, and then we are outer approximating the objective function at the points xk and yk, right? So basically, xk and yk are for example, those points you choose to outer approximate the boundary of the convex region. And then you pick the same points to outer approximate the constraints as well. Right? So this is called the MILP master problem. And as you can imagine, it is a relaxation of the original problem. Right? So you are kind of relaxing the nonlinear constraints by a finite number of linear constraints, basically. Okay. And since you have so many cuts, you need to define a variable for the objective, right? So the objective has to be greater than or equal to all the under approximators of the objective function. So geometrically, it's like you have a bunch of linear underestimator. The objective has to be greater than or equal to all the underestimators. Right? That's basically what this equation is doing here. And for the constraints, we just outer approximate all the constraints using the linearization points xk and yk. Yes?
Can you explain what gamma is again?
Yeah, so gamma is a variable to represent the objective, right? So since you have so many linear outer approximation, you cannot put those directly in the objective, right? So essentially you are replacing the outer approximation with, So essentially what this function, convex function, is that you want to use some OA type of cuts such that this function is greater than or equal to all the linearization cuts you generate, right? As you can see, they are under approximating this convex function, and this function is greater than or equal to all the linearization cuts you generate, right? So essentially this gamma, which is the objective, should be greater than or equal to all the linearization cuts.
So m is the original objective function, essentially.
So yeah, so we can treat gamma as the not really the yeah, you can treat gamma as the original objective function, but in this case we are doing an approximation of the original objective function. Right? If you have infinite number of cuts here, then gamma would be the original objective function. But since you are only have finite number of them, you can treat gamma as a max of a bunch of linear functions.
Okay.
Okay. Yeah. Any other questions here? Okay. Yeah, so in practice, you only need to outer approximate the nonlinear constraints, right? The linear constraint, even if you do an outer approximation, it will be the linear constraint itself. It doesn't really matter. All right, so the next question is, I ask you this question, where we should choose those outer approximation points, right? That's the most essential question to answer. Right? If you already know how to pick the outer approximation points, perhaps this will just converge in one iteration. But we actually don't know, right? So in the outer approximation algorithm, okay, yeah, so let's first talk about this question, right? So in the first iteration of the outer approximation algorithm, let's assume there is no cuts being added, right? So all the nonlinear constraints have been removed. So if you remove all the nonlinear constraints, you may have an unbounded problem, right? So essentially, if you are looking at this problem, if you don't add any outer approximation cuts, then this will be an unbounded region, right? If you just remove this nonlinear constraint here, the problem region will be unbounded. So in that case, in the first iteration, at least you need to select some outer approximation cuts to make the problem bounded. So usually what people do in practice is that you first solve a relaxed nonlinear programming problem. So here means you are relaxing the binary variable to continuous variable, right? And then you solve this convex nonlinear programming problem and use the solution of this convex nonlinear programming problem to generate outer approximation cuts. Right, so the solution of this nonlinear programming problem, let's denote them as X node and Y node, and then in the first iteration, you just generate outer approximation cuts at these points. You look a bit confused. Any questions?
I'm sorry, so we're relaxing Y to be a continuous variable?
Yeah, so you solve this problem, yeah, relax Y to be a continuous variable, solve this problem, then you get, some points to do the outer approximation cuts, but because you don't know where you should add those outer approximation cuts, right? So in the first iteration, you just add those cuts, usually that can give you a bounded problem. Otherwise, if you just relax all the nonlinear constraints altogether, the problem might be unbounded. Okay. So after that, what you will do is that you will iterate between an MILP master problem and an NLP subproblem. Okay. So the MILP master problem is an MILP, right? You solve this problem, and then you will get an optimal value of both the X and Y variable, right? Then what you will do is that you will fix the Y variables to the optimal value, optimal solution of the MILP master problem, and then you solve the rest of the nonlinear programming problem, right? So now the binary variable have been fixed. The rest of the problem is a convex nonlinear programming problem. Right? So you just solve the rest of the problem. It only have the continuous variable X. Yeah, so but in some cases, when you fix a binary variable to YK, the nonlinear programming subproblem might be infeasible. Right? If you just pick a YK, although it's feasible for the MILP master problem, it might be infeasible for the convex nonlinear programming problem. because the MILP is a relaxation of the nonlinear constraints. Right? So if you just fix y to yk, you might be getting an infeasible solution. So what you will do in practice is that you will add a u like a slack variable to the on the right hand side of this problem, right? So here it's like you have a less than equal to 0 here, but if you add a slack variable u here, even if the original problem is infeasible for sufficiently large positive slack variable, you will always get a feasible solution. Right? And of course, you will be minimizing the value of the slack variable in the objective because you want a solution that is, quote, as feasible as possible.
Is
Yeah.
there a way to fix the slack variable so we can avoid reaching an infeasible MLP? I mean, which value of the slack variable should be?
Yeah, so the slack is the variable you are optimizing here, right? So you are trying to find a slack variable that makes the NLP feasible. Actually, you are trying to find the smallest slack variable such that the NLP is feasible. Okay, so that's what you are doing here. So here, maybe I should write down you are minimizing over u and x here. Here you are just minimizing over x. Okay. Is it clear or not? Some of you look very confused. You probably should ask a question. I thought this is a very easy part of this lecture. If you are, yeah, if I didn't explain it very well, please ask a question. Then otherwise we cannot proceed. So maybe to summarize what we are doing here, right? So the MILP master problem is a relaxation of the original problem, right? You are relaxing the nonlinear constraints, but you add some first order Taylor series expansion type of cuts, right? So you first solve the MILP master problem. After you are done with that, you got the value of the binary variable and the continuous variable, right? So since the MILP master problem involve both x and y, right? The continuous variable and the binary variable. After you solve it, you get the optimal y variable, right? And that's called the optimal solution to this MILP master problem to be yk. So let's say yk is the optimal solution. Right, so you solve the MILP, get the optimal solution, then you fix the y variable to be the value of yk, right? You just got from the MILP master problem, and you solve the nonlinear programming subproblem, right? Since now the binary variable have been fixed, you are left with only the continuous variable, right? Then you solve this continuous nonlinear programming problem, you get the optimal solution of x. So if you are lucky, this this NLP subproblem is feasible, right? But on the other hand, if you pick a binary variable y that make this NLP subproblem infeasible, it could happen, right? Because when you obtain the yk, you are relaxing a lot of constraints, right? You are just doing the OA type of constraints. So that's why yk might be infeasible. Although it's feasible for the MILP, it might be infeasible for the nonlinear programming problem. Then you need to add some slack variables such that you get a feasible solution from the subproblem, right? So you can imagine this is like maybe not a good analogy. Is that the U is like a big M parameter that relax your relax all the constraints you have. You want to find the smallest big M parameter to relax this constraint, right? Yes.
So when you solve the initial MILP, are you not getting like optimal X?
Yeah, that's a good question. That's how do you do it for the extended cutting plane methods.
Okay.
But now we are not taking the optimal x from the MILP. We are only taking the optimal y.
And then resolving it.
and resolve the NLP. I will
Okay.
explain why we want to do that later.
Okay.
Yeah. Okay. Yeah, that's a good point. You already kind of invented a new algorithm just by looking at this. Okay. Yeah. Any other questions? Okay. Yeah, so maybe I have to skip some of the stuff. I didn't expect this is not so straightforward to digest. But let's go through the methods, right? You first define an initial MILP, right? The way to define an initial MILP could be the way I talked about in the previous slide. Yeah, so if you don't quite get it, just look at the main thing we are doing in this while loop, right? Basically, there are two optimization problems we solve, right? So if you don't care about the infeasibility situation I talk about, right? If you don't quite get it, let's just talk about in the simplest case. You are always lucky. You will never have a problem which is unbounded. You never have a problem that is infeasible, right? So let's say we are in the luckiest case. Just to get the gist of the method is that you will iterate between the MILP relaxation. The MILP relaxation is an outer approximation of the original non-convex region. That gives you a lower bound, right? Because we are relaxing the nonlinear constraints with some linear ones, right? And then you can fix the solution from the MILP relaxation, call it YK. Then you solve the NLP relaxation by fixing the YK you got from the MILP. Then you obtain the continuous variable xk, right? So if the NLP is feasible, do you get a feasible solution to the original problem? Anyone? Why do you say no? So what does feasibility mean, right? Feasibility means first you satisfy the binary constraint of the y variable. Second is you satisfy all the nonlinear constraints, right? Those are the two constraints we talk about. So if you solve the restricted NLP problem and you get a feasible solution, is it feasible for the original problem? It is, right? Yeah, so because by solving the NLP, you are guaranteed to satisfy the nonlinear constraints. And YK is obtained from solving the MILP relaxation, right? In the MILP relaxation, YK have to be binary, right? So you satisfy both constraints by solving the NLP, right? And then the MILP gave you a lower bound because you are relaxing the nonlinear constraints, and the NLP gives you an upper bound. So if you couldn't get the details, at least get this part, right? You are decomposing the MILP into two problems. One is the MILP, one is the NLP, which give you lower bound and upper bound respectively. Okay, at least get these two parts. Then the details you can check the slides again and try to digest that. Yes.
I'm sorry. Why does the NLP give you an upper bound?
So the upper bound here means a feasible solution, right? That's what I mean, right?
Okay.
Because by being a feasible solution, there are two types of constraints, right? The nonlinear convex constraint and the binary constraint, right? And you can easily check they are both satisfied by solving the NLP, right? First, the YK is binary, right? Because it's a solution of the MILP problem. Second, by definition, when you are solving the NLP, you satisfy the nonlinear constraints. So all the constraints are satisfied. Okay. Right? Yeah.
So can the numerical value of UB be lower than NB?
The UB be lower than, why do you say that?
I'm asking, can that be the case? Because because if it's not an upper bound, so it's called an upper bound, but it's not actually an upper bound, right?
Why it's not?
Because you just said, that it is only satisfying the...
Yeah, so if it is a feasible solution, it is an upper bound, right?
Yeah.
Right, so any feasible solution to an optimization problem is an upper bound of the optimization problem, right?
Yeah.
Right. So why do you say that could occur, would happen?
No.
You get it?
Yeah.
No.
I just got confused.
You got confused. Oh, okay. So then probably I have to spend half an hour. Yeah. So we can talk later. But any feasible solution, we are minimizing any feasible solution is an upper bound, right? And the lower bound, by definition, is a lower bound of the optimal solution, right? And why can an upper bound be? Otherwise, it is not called an upper bound. It is not called a lower bound, right? Yeah. Okay.
But it's a maximization problem then?
Yeah, it's the other way around. Yeah, it's the other way around. Yeah. Okay. Then I don't know if I can proceed with the lecture now. So let's skip the convergence. I was going to, the beauty of the outer approximation is in its convergence. But since people already got confused with the algorithm, probably I should skip this part. Maybe just a gist of the convergence is that the OA will converge in a finite number of iterations, right? So there are numerous ways you can add the outer approximation class, but it has been proved that the outer approximation will always converge in a finite number of iteration. Why is that? Because you will never revisit the same binary variable again in the MINLP master problem. Once you visit a given binary variable, it's like it has been cut out. You will always encounter a different one until you converge. Okay. Yeah, so there are some proof hint. Well, if you are interested, you can take a look. So let's say any final questions on the OA? Yes.
So when you're solving the MILP and you solve the value for like a binary variable, does it stay the same, like the optimal value for a binary variable, does it stay the same between every iteration? Is that the idea behind the convergence?
Let's say that again.
So like when you're solving like the optimal value for a binary variable when you solve the MILP, right?
Yeah.
So that value stays the same at every iteration, or no?
No, it doesn't. Because you are keep adding cuts.
Okay.
Right. Since the MILP is an outer approximation, as you add more cuts, the lower bound will always increase.
Okay.
Right. So you are constraining the problem more.
Okay.
Yeah. Okay.
But it's in the particular case of the convex and non-convex problem.
Yeah. For non-convex, we will talk about that at the end. Okay. Yeah. Yeah, so now let's, I have to go to the next slide. Let's talk about generalized Bender's decomposition. So the original paper was written in 1972, right? I read the original paper when I was like a first-year graduate student. I spent months on reading the original paper. It is still unreadable to me until today. So we will show you a much easier derivation than the original paper, but it is more a dumbed down approach of deriving that. Right? The original paper is much smarter. So you feel free to take a look at the original paper if you wish. So here we will show you a very easy proof of how to derive the generalized Bender's decomposition. So recall that in the outer approximation methods, we are adding outer approximation cuts, right? So basically, in each iteration of the outer approximation algorithm, we are adding, let's say, we have one objective, and then we have m constraints, right? So basically, in each iteration, you are adding m plus 1 constraints or cuts, right? That's what you do in the outer approximation methods. But the generalized Bender's decomposition is saying that I don't want to add so many constraints, right? Can I just add a single constraint in each iteration, right? So in other words, we will be solving the same subproblem. You will still solve the same nonlinear programming subproblem, right? But the master problem will be changed by two different aspects. The first thing is that we only want to add one single constraint, right, instead of m plus 1 constraint. The other thing is that we want to add the constraints only in terms of the binary variable, right? So in that case, in the master problem, you will be only solving an optimization problem with binary variables. There is no continuous variable in the master problem, right? So again, two differences. One is that in the Bender's master problem, you will only have binary variable. There are no continuous variable. That's number one. Number two is that there is only a single cut per iteration, right? Okay, so how we are going to do that? Of course, as you can imagine, right, we will do some aggregation of those constraints, right? In the OA class, we add m+1 constraints, and then we want to aggregate them in a way that we only add a single constraint, okay? And just to write it out, since here I'm talking about the gradient of this function f, then you can write it out as the gradient over x and the gradient over y times x minus xk, y minus yk. Right? This is just a rewrite of the original cuts, and then for the constraints we are doing the same thing, right? Yeah, and then we are just writing down the the gradient in terms of x and the gradient in terms of y. That's what we are. That's just a rewrite of the constraints. Okay, so now what we like to do is, I said, right, we want to do two things. One is that we want to aggregate these constraints such that we only have one single constraint. Second thing is that we want to remove all the terms related to x, right, such that in the master problem you only have the y variables. Okay, so keep that in mind. Yeah, so maybe I should scroll it this way. Okay, so how we are going to do that? So recall that when we solve the nonlinear programming subproblem, right? So as I said, we are solving the same nonlinear programming subproblem in Bender's and Alter approximation. Basically, you fix the binary variable to be a given value yk, and then you solve the rest of the nonlinear programming problem, right? So this nonlinear programming problem is a convex problem, right? So in the optimal solution of this problem, you need to satisfy the KKT conditions, right? Hopefully everyone is familiar with the KKT conditions. We got an exam question on that, right? So let's if you write down the KKT conditions of this problem, there is only a problem related to the x variable. Then you can write down the stationarity conditions. Is nothing but this thing, right? The gradient of with respect to the objective function times the all the Lagrangian multiplier multiply the gradient of each constraint. They have to be equal to 0, right? This is a stationarity constraints. And since this whole thing is a vector in the same dimension of x, right? So if you multiply this by x minus xk, right? So this whole thing is a 0 vector. The 0 vector multiply any vector is 0, right? So you just multiply them by x minus xk. Okay, so now you arrive at the sum over an aggregation of the gradients equals to 0, right? And plus the objective. Okay, so why this KKT condition is useful? The reason is that we can use the KKT condition to get rid of. Okay, hopefully this is not too small. So as I said, in the Alter approximation cuts, we have m+1 constraints, right? And you have some terms related to x, right? And we want to get rid of those terms related to x, right? What I told you is that in the Bender's master problem, we only want to solve a problem with respect to the y variables, right? So that means you have to get rid of all the terms related to x, right? So how do you get rid of those terms related to x? You can compare this with a formula we derived here, right? So you can get rid of the x term by aggregate some of the constraints such that all the x term will cancel out and they sum to 0. Okay, so you can try to do the math yourself. So the way to do that is you can multiply the first constraint by 1, and you multiply all the all the other cuts by the optimal Lagrangian multiplier, right? And you sum them up. And then you'll quickly find out that when you sum them up, all the terms related to x will be canceled out, and then you can get this form, right? Related to this is called the generalized Bender's cut, which only have the binary variables. Okay. So I talked through this very fast. Maybe you should do a derivation yourself. I remember when I studied it, I at least spent a couple of days just on the derivation. So it wouldn't be possible that we make it very clear during class. Right? So the whole idea is that you do some aggregation of the constraints, and then you can cancel out some of the terms. Okay. Yeah. So here, just to summarize what we did here is that in generalized Bender's decomposition, the difference is that the form of the cuts are different, right? In the outer approximation, you are adding m+1 number of cuts, but in generalized Bender's decomposition, you are only adding one cut per iteration, right? Because and then the generalized Bender's decomposition cut is weaker than the outer approximation cuts because it is an aggregation of the outer approximation cuts, right? So you're multiplying each constraint by the Lagrangian multiplier and add them up. So as a result, since the cut is weaker than the outer approximation cuts, generalized Bender's decomposition usually takes more iterations to converge, okay? And then when the nonlinear programming subproblem is infeasible, we are going to solve similarly this type of problem with a slack variable. And in the literature, the cut that are derived from this type of problem is a so-called feasibility cut. So they can cut off your infeasible solutions. Okay, so maybe before we go to the next one, any questions for the GBD, at least for the intuition, if we are not getting the algebra correctly. Right? So the idea is that you don't want to add so many cuts in a given iteration, and then you don't want to solve a large MILP problem. You only want to solve a problem with pure binary variables. There are no continuous variable in the master problem. But the downside is that you take more iterations to converge. Right? Okay. Yeah, so now we will talk about the algorithm that Jatni already suggested called extended cutting plane method. Right? So here the idea is quite simple, which is, after you solve the MILP master problem, why do you bother to even solve a nonlinear programming problem again, right? Why don't you just linearize the nonlinear constraint at the solution of this MILP master problem, right? So since the MILP master problem in the outer approximation have both the x and the y variables, after you solve the problem, you will get a solution, right? So if you get a solution xk and yk, you can linearize the nonlinear constraint just at the solution of this MILP master problem without even solving the nonlinear programming problem. Okay. Let's say, so the difference in the extended cutting plane and outer approximation is a way you are going to linearize those constraints, right? In outer approximation, you solve a nonlinear programming problem and then use the solution of the nonlinear programming problem to linearize the constraint. But in extended cutting plane, you just solve the MILP master problem and use the solution of the MILP to linearize the constraints. Okay, so what does that mean in practice? In extended cutting plane, the point you choose to linearize the nonlinear constraint may not be a feasible for the nonlinear constraint, right? So you can look at these pictures like this. So here in this ellipsoid shape, let's assume it is your nonlinear constraint, right? But then you are going to linearize this nonlinear constraint at a point of the solution of the MILP problem, right? So the MILP, you can think about the, let's say, you have an arbitrary outer approximation of this nonlinear region, right? So let's assume this polyhedral is your outer approximation region, right? So you have the MILP master problem. After you solve the MILP master problem, you may hit this point here, which is not NLP feasible, right? So because you didn't solve the NLP subproblem, the point you get from the MILP master problem may not be a feasible solution of the NLP, right? And if you choose this point to linearize the constraint, you are not getting a so-called supporting hyperplane of the nonlinear constraint, right? So instead, if you move it inside, this cut will be much tighter than this cut here, right? Okay. So that's a downside of the extended cutting plane method, is that the outer approximation cuts you generated are not so-called supporting hyperplane of the convex feasible region, right? The reason is that you didn't solve a convex NLP problem. And usually ECP takes a larger number of iterations than outer approximation to converge. Okay, so to address this challenge, there has been an extension of the extended cutting plane method called extended supporting hyperplane method. And the high-level idea is the following. You can pick an interior point of the convex nonlinear region, and then in the ECP method, you may get some point that is outside this nonlinear region. You can do a sort of like a line search such that you pick a point which happens to be on the boundary of this nonlinear region, right? So you can think about you do a binary line search on this line segment between the MILP solution and an interior point. And then you just pick this point to linearize the constraint. This will give you a much tighter cut than you do an outer approximation at this point. Okay, so that's an intuition of the extended supporting hyperplane methods. So how do you actually implement the extended supporting hyperplane? First of all, you need to find an interior point, right? So I talk about this interior point of the convex nonlinear region, but we need to find that interior point, right? So one of the ways we can find the interior point is by solving an optimization problem. So here, as you can see, U is no longer a slack variable here, right? So here U is representing how far you are getting into each of the constraints. Okay, so mu is a variable that is in R1, right? You don't have U to be greater than or equal to 0, right? So you are kind of minimizing. So should be perhaps be. Yeah, so you should be minimizing U, okay? So you are going to minimize the right-hand side of each constraint such that you get the tightest constraint possible here, right? And here U is unconstrained. It will give you a strictly feasible point of the NLP, okay? Maybe let's explain this a little bit, right? So let's say, to give an example, if you have a constraint saying that, x squared minus 4 less than or equal to 0, right? That's a nonlinear convex constraint you have, and then you can add the U to this problem. U is in R, and then you have maybe let's give some. Okay, so there might be other constraint for x that we don't write it out explicitly. So suppose you solve this optimization problem, and you find out the optimal u value is -2. Okay, so that means you get a point that is even tighter than the original constraint by 2. Right? So the right-hand side is switch from 0 to 2, you get an interior point of the original constraint. Okay, so it's essentially saying this constraint is like, x squared less than equal to 4 is essentially a circle where, the radius of the size circle is 2, right? If you get u equals to -2, essentially you are saying that I can get an interior point at the origin. Right? That will give you a feasible point, strictly feasible point of the MINLP. Yeah. So now, with a strictly feasible point, which is this x interior, y interior here, and then you have the original solution of the MINLP master problem denoted by x MINLP and y MINLP. Okay, so as I said, with the interior point and the this MINLP point, we want to find a point that is on the boundary of the convex nonlinear constraint. Right? So how to find the point on the boundary? The way we do it is we define a function called capital Fxy, which is a maximum over all the constraints, right? So that says, let's say, so the max over gi of x and y is essentially saying that I'm going to pick the constraint that has a maximum violation, right? Okay. So then, as you can imagine, when this capital F function equals to 0, that means you are at a boundary, right? Because that says the max violation of all the constraint is 0. So you will do some line search such that, pick a lambda such that this capital F function is 0. Then you know that this combination will give you a point at the boundary of the feasible region. Then you can linearize all the active constraints at the boundary of the feasible region that give you supporting hyperplane instead of the extended cutting plane method, which may give you a non-supporting hyperplane. Any doubts? Okay. Yeah, so now let's talk about an extension to the outer approximation methods, right? Just to refresh your memories, in the outer approximation, we are solving two problems, right? The MINLP master problem and the MINLP subproblem, right? But the issue is that whenever you solve the MINLP master problem, you need to do the branch and bound from scratch, right? So you are not taking advantage of any information you gained from previous iterations. Right. So this LP-NLP based branch and bound proposed by Quesada-Grossman is to address this issue. The idea is to say, I only want to do a single tree branch and bound. Instead of solving multiple MINLPs, I just want to solve a single MINLP without iterating between the MINLP and the NLP subproblem. Okay, so this is so-called single tree outer approximation method, where we only have a single branch and bound tree. Yes, I'm not going to the details. The way you can think about this, this is implemented is that suppose you have an MINLP master problem, you start doing branch and bound, right? At the root node, you just solve the root node linear programming relaxation. And as you do the branch and bound, you may get a feasible solution to the MINLP master problem, right? So that is integer feasible. And whenever you get an integer feasible solution to the MINLP master problem, you will solve an NLP subproblem, right? So remember in the OA methods, once we get the optimal solution to the MINLP master problem, we will solve an NLP subproblem. Here is saying that let's just do this dynamically, I will solve the MILP master problem. Whenever I encounter an integer feasible solution, I will call an NLP solver and then update all the nodes in the branch and bound tree by adding the OA cuts.
Can you explain that one more time?
Yeah. So here, the motivation hopefully is clear, right? You don't want to do multiple branch and bound. You just want to do a single tree branch and bound, right? And then let's imagine at iteration 0, you have an MILP master problem with only a bunch of outer approximation cuts, right? And you start solving that MILP master problem. At some node, you are going to have you are going to encounter a feasible solution, right? Because the MILP is feasible. And once you have a feasible solution, that means all the y variables are binary, right? That's by definition a feasible solution. And then whenever a y variable is binary, you will fix a binary variable and use a nonlinear programming solver to solve a convex nonlinear programming problem simultaneously as the branch and bound tree goes, right? Okay. So after you solve the nonlinear programming problem, you can add outer approximation cuts based on the solution of the nonlinear programming problem, right? Okay, so after you solve the nonlinear programming problem, you will add OA cuts to all the nodes, not only the nodes you find the integer feasible solution, okay? And then as you go on, the convergence is not that trivial. You will find out that whenever you have a feasible solution, you will add OA cuts to it, right? At the end of the day, when all the you can imagine all the integer feasible solution has been certified by the outer approximation cut, right? And at that time, you will run out of feasible solutions where you have some convergence limit of the upper and lower bound, and then you will converge. Okay. Yeah. But implementing that is non-trivial. So if you want to implement that, you will need something called lazy callback from the solver, right? Because in order to implement that, actually you want to interfere with the branch and bound process, right? So nowadays, when you guys solve an optimization problem, you just call Ruby, solve an MILP for me, then it will solve the problem, right? Here it's saying that I want to know whenever I find a feasible solution in the MILP, then I want to have a separate process that solve a nonlinear programming problem for me. Right? So implementation is not so trivial for the Quesada-Grossman. We will spend one whole lecture on the solver callback at the end of this course. Right? So there are a lot of problems where you do want to interfere with the branch and bound process by adding some things like cutting place. Okay.
And it adds this to all the active nodes?
Yeah, all the active nodes.
Okay.
So actually you can choose, in there is a solver option, you can choose whether you want to add to all the active nodes or just the node where you find the feasible solution.
Okay.
Okay, yeah. Okay, so I think this has been asked already. How do you extend outer approximation to non-convex problem, right? So one of so I will talk about a very naive extension. They are more sophisticated extension. Right? So let's geographically, from this figure let's say how it works, right? So you have essentially the feasible region is this green region here, where even the relaxation, the NLP relaxation is non-convex, right? So you no longer have a convex function to do the outer approximation. So the naive idea is that's first convexify the nonlinear functions by a convex nonlinear function, right? So that's this blue line here. And then you can do outer approximation on those convex functions, right? Okay, so now you kind of convert a non-convex MINLP to a convex MINLP, right? Then you can use the outer approximation to solve that convex MINLP, right? Of course, that's not equivalent to the original non-convex MINLP. Okay, but then how do you solve this to global optimality, right? If you don't have the original problem. So there are two things that you can guarantee global optimality is once you find a binary solution from the convex MINLP, you will use a global optimization solver to solve the non-convex MINLP, right? So that gives you an upper bound, which is a feasible solution to the original problem. But how do you guarantee you don't repeat or you don't cycle over all the binary solutions, right? Because the worst case scenario is that you find all the binary variable combinations and you solve the non-convex MINLP to global optimality using a global solver, right? And then in order to make sure you don't cycle, we need to add those so-called no-good cuts or integer cuts. So if you have done one of those homeworks, you probably will remember this form. It just says, if you want to cut out a given binary variable y, where all the yi in the set B equals to 1 and all the y in the set N equals to 0. And if you add this type of cut, you will cut out this particular binary variable combination, right? So in the worst case, you will just exhaustively enumerate all the binary variable, okay? And you are hopeful that if this convexification is very tight, you don't need to enumerate all the binary variable combinations. Yeah, so this is optional, not really required. So finally, if you don't really care about the methods, how do you use those methods, right? So you can, the Decomp is the first ever MINLP solver out there that implement outer approximation methods. And you have alpha ECP that implements the extended cutting plane method. Short is a solver that implements the extended supporting hyperplane methods. So MINLP is a recent solver in Pyomo developed by our own professor David Burnell and his postdoc Zedong Peng, who are both in our department right now. So they implement a solver in Pyomo for outer approximation and Quesada-Grossman methods. Now I think there are some extensions to non-convex outer approximation as well. So if you have Pyomo installed, you already have I think you already have MINLP installed on your computer. Okay. So here's so if you want to know a benchmark of all the convex MINLP solver, you can check this paper by Jan Krokvist, who developed this solver short, and our own professor David Burnell, who developed MINLP. So they did a benchmark on different convex MINLP solvers. Then here are the references. This is the reference for the outer approximation, and we have generalized Bender's decomposition. And then, this is a reference for short. We have the non-convex OA and the single tree outer approximation. So I think we still have around 15 minutes. Maybe I went too fast. So anything that is unclear, we can go back to talk about it again if you wish. So can I take it as everything is clear or everything is unclear? Yes.
Can we go back to, I think it was the extended sequence.
Yeah.
There was when f is equal to 0, it's the boundary. I didn't understand this. No,
Yeah, so if you,
Yeah, this one.
This one, yeah. So when f is 0, it is a boundary, right? So then basically you have the original constraints are g at x, y less than or equal to 0, right? So when a constraint is 0, that means a constraint is active, right? So if you take the max of all those constraints, that's saying I want to get the most violated constraint, basically. Yeah. Yes.
So for the OA algorithm,
Yeah.
I guess when you add the slack variable,
Yeah.
what's its purpose? I understand it exists, but when you describe the algorithm, I guess I think it's slide 6. Yeah, right there.
Yeah. So what's the purpose of adding the slack?
Yeah.
Okay, yeah, sure. So here, the reason you want to add the slack is that you first solve the nonlinear programming problem, right, by fixing the binary variable to yk. Yeah. And then if you solve this problem and it is infeasible,
Yeah.
right, So now you want to make it the problem at least feasible, right? So here, in the original constraint, you have GL of x less than or equal to 0, right? So you know that if you enforce this constraint, it will be infeasible, right? But if you add, let's say, a positive number on the right-hand side, being, let's say, GL of x less than or equal to 2, it's a weaker version than gx less than or equal to 0, right? But then what do you want to add to the right-hand side to make this problem feasible, right? You don't want to add a too large number. It's like in the big M, if you add 10,000, maybe it's feasible, right?
Yeah.
So that's why you want to add a U variable here. U is a positive number. It's like the constant you add to the right-hand side to make it feasible. And then in the objective, you minimize the U. It's saying, what will be the smallest slack you should add to each constraint such that the problem is feasible.
So is that used in future iterations of the problem?
Yeah, so because in the original problem, you couldn't get a solution, right? You couldn't get an xk from the original problem. But if you solve this problem with a slack variable, you are guaranteed to be feasible, right? You just pick the U value to be large enough.
Yeah.
Right, so with this you will get a solution from this NLP, and then you use the solution of this NLP to linearize your your MILP master problem.
Okay.
Right. Of course, there is a theoretical reason in doing that. Then you have to show what properties those have, and similarly in generalized benders, the reason you want to add the slack is that you can show it will cut off the previous infeasible solution. Okay, yeah. And in most of those proofs that require things like KKT conditions and Lagrangian duality, which I didn't cover the convergence of the OA. Maybe we can talk about it really briefly if you guys are interested in how to show the convergence of the OA, because I don't want to make you too confused in the first round. Yeah, any other questions?
I'm sorry. Why not just cut off the solution from the NLP? Why do you do that? Like, why do you go through the trouble of adding slack?
Yeah, so that's a good point as well, right? So when you evaluate how good a cutting plane is, so there are also, we talk about how tight a cutting plane is, right? So you can also argue in the following sense, right? Why do you bother to add outer approximation cuts? Why don't you add, where do I have it? The no good cuts, right? So this cut is saying that basically what this cut is doing, if you don't look at the formula, I can tell you in words, right? What this cut is doing is that don't give me the same binary variable again, just give me a different one, right? Okay, so that's what this cut is doing. Right. But why do you bother to add the outer approximation cut instead of this cut here? They are doing the same thing, right? You don't want to get the same binary variable from the master problem again. So that has to do with the tightness of those cutting planes, right? So this cut is called a very weak cut because it only cut out a single binary variable for you. But in the OA, in practice, it's much better than this type of cut. That's a key to why do you bother to solve a nonlinear programming problem.
So in solving for the slack variable, we're essentially creating a better cut.
Yeah, so you can get a better cut from the outer approximation.
That constraint.
Yeah. So that basically by solving the nonlinear programming problem, it gives you a very good point to linearize the nonlinear constraint, right?
Okay.
So because you don't know where to linearize, and then we can show that by linearizing from the NLP subproblem, you get very good linearization points, quote, good linearization points.
Is that the equivalent of being like on the boundary of your feasible region, I guess?
Not only on the boundary is one thing, but the other thing is optimality. Right? Okay. So you are solving the nonlinear programming problem to optimality. Right? Given a binary variable, you are getting the best continuous variable for that binary variable. So that's a good point to linearize. Okay. Yeah, so it has to do with, if I can have a lot of time, I can explain the convergence of OA. So if you try to read the convergence of OA, you will find out that, after adding so I can talk about this very briefly, why outer approximation converges, right? So maybe before we talk about why outer approximation converges, a question you guys can think about is that what would be the scenario it doesn't converge? Actually, when this algorithm was developed, a lot of people thought this is a heuristic, it doesn't converge at all, right? So what would be the case that, let's say we don't have the convergence proof here, you don't know whether outer approximation converges, right? So what would be a instance that, what would be a situation where outer approximation fails to converge? Right, so you are solving MILP and then you solve the NLP. The MILP always give you a lower bound, the NLP always give you an upper bound, right? But you have to show that the upper bound and lower bound actually will hit each other at the end. Okay. Just think about that for, let's say, 30 more seconds to see if anyone have an answer.
In case if the sequences don't converge to a single value.
Right, so when would this, because we have the sequence has finite number of choices, those are binary combinations. When would the sequence doesn't converge? Okay, so I actually write it down here, right? So the OA will not converge if, let's say, you solve the MILP master problem, you get a binary variable, right? And you go back to solve the NLP problem, add the OA cuts, right? And for 2 consecutive iterations, the MILP master problem give you the same binary variable, right? So if for iteration k and k plus 1, you got the same binary variable, right? Then you will add the same OA cuts again, because the OA cuts is added by fixing the binary variable, right? So for 2 iterations, if you encounter the same binary variable, you must show it already converges, otherwise you will be stuck at this binary variable.
Is that not the same as saying that that's your optimal solution?
Yeah, so you have to show that if for 2 consecutive iterations, you got the same binary variable, right, in the MILP master problem, that has to be the optimal solution,
Okay.
right? So in other words, in that iteration, the value of the MILP master problem should be equal to the value of the NLP subproblem, right? So how do you show that? You can show that by checking the KKT conditions of the MILP problem and the KKT conditions of the NLP subproblem, and you can show that they are essentially equivalent, right? And then you show with that you can show that their objectives are the same. You can find a KKT point of the linear programming problem restricted as y equals to ik by using the same KKT point of the nonlinear programming subproblem. So that's a trick here.
And if the KKT conditions aren't satisfied, then you can't converge, essentially.
Yeah, so essentially, the nonlinear programming problem always satisfy the KKT condition, and you can show that by adding those OA cuts, it at least will give you, at the optimal point. Okay, so maybe let me say it in a more clear way. So you have an MILP master problem where you have added a bunch of outer approximation cuts, right? So what you want to show is that if I fix y at yk, all the yk I have encountered before, right? If I fix y at yk, now it becomes a LP, right? So if you fix all the binary, once you fix all the binary variables, then the LP have to satisfy the KKT conditions. Then you can show that once I fix y at yk that I have encountered before, the LP will give you the same value as the NLP, right? So that kind of show you the lower bound fixed at a given point will always give you the value at the NLP solution. So that's a gist of this convergence proof. And why the cuts are effective is because you can make this type of argument. Once you encounter a given binary variable, you won't cycle again. Okay. Yeah, so you can check the math to see if I lied. Yeah, and then any other questions? Okay. So it's totally all right if you don't understand 100% after the lecture. Usually, you need to spend days or even months trying to digest everything. Yeah.